Okay, welcome to the cracking hydrocarbons video. And what we're going to be looking at here is the reason behind why we crack hydrocarbons. Remember from previous experience and videos and what you probably read in textbooks, etc., that hydrocarbons are those compounds made up of carbon and hydrogen. They're found in petroleum oil, and we did learn that in our petrol oil, we cracked it into different fractions based upon boiling point. We saw that in fractional distillation of petroleum oil, that as we move up the column, we go from heavy chain fractions all the way up to the lighter refinery gases. But why do we crack? Well, the thing is that we get our petrol from petroleum, and there is not enough petrol length fractions in petroleum when you separate it out to satisfy the societal demand. Okay, we have a lot of cars that need this, and we don't have enough within the size of the fraction to satisfy demand. So I guess the first thing, and write this down of course, right, to make more petrol length fractions. And the reason why is because the percentage of petrol length fractions in petroleum is not enough to satisfy demand. So let's say, what do we mean by cracking? Well, cracking is breaking something apart and making it smaller. Okay, so that's what we want to do here. Let's say we start off with a pentadecane, which is 15 carbon molecule, and we want to break that down into smaller components. So we might break that down into a propane, to some ethanes, and maybe an octane. Okay, and so we have one octane, we have two ethanes, and we have a propane. So the numbers at the moment just represent the size of the carbon molecules, not actually how many we have on each side. So they're not going to equal each other up at the moment. So we're basically breaking a 15 carbon chain down to multiple smaller units. So this is called cracking. And there's two main types of cracking we're going to get into. One's called thermal cracking and one's called catalytic. The second reason why we want to crack larger fractions is to make ethene. And the common name for ethene is called ethylene. And why do we want to make it? We want to make ethylene so it can be used as a feedstock for industrial processes. So what do we mean by feedstock? Well, feedstock is the starting chemical of a process. And so if the process is, let's say, making a polymer, we're going to learn that we're going to make some PVC, some polyvinyl chloride. We need to start with a chemical to start making that process, and that chemical comes from ethylene. So ethylene is the feedstock that supplies the basic raw materials for that process of polymerization. And we need to make ethylene. Now, what we have to remember here is we want to sort of break our thinking apart, that when we crack petroleum, if we're wanting to make petrol length fractions, that is 8 carbon chains, that is the desired product. That's the desired product. So these two here can be thought of as waste products, I guess you could call them, or byproducts would be a better name, right? So this is the desired product because that's what you're after in the process. These are the byproducts. And so in this instance, ethylene can be considered as a byproduct. However, we can crack ethane into ethylene, right? So ethane is a alkane, and we can crack that into ethylene. Since this here is the desired product, it's not considered a byproduct, it's the main product we need. So we can make ethylene in two different ways. We can grab it as a byproduct from this process, or we can change the material that we start with. Instead of it being a 15 carbon, we're actually cracking or breaking a bond here to make a desired product. So still cracking, but here we're starting with ethane. So we're taking some of the refinery gases that we have in the fractional distillation and we're cracking it into ethylene. So the whole purpose behind cracking, one, is to make more petrol length fractions because they don't satisfy demand, so we need more of them. And the second one is to make a feedstock ethylene. Okay, so make sure you get all that down, and we're going to be drawing a flow chart and looking a little bit more in depth about these processes. So we just had a quick overview there. Now let's delve in a little bit more detail, and I like to create some flow charts because they're easy to understand and helps diverge your thinking and makes things very clear. So we said that cracking can be two main reasons. The first reason is to increase petrol fractions because the amount we have doesn't satisfy demand. And then of course we want to make some ethylene as a feedstock for other chemical processes. So if we think of increasing it in terms of the amount of fraction for petrol, there's two main processes that do this. The first one's called thermal cracking. Now in this video we're going to be looking at thermal cracking. The next video we're going to be looking at catalytic cracking. And then the video after that we're going to be looking at the processes of making polymers from ethylene. Okay, and so one of the main polymers from ethylene is to make, I'll put this here, polymers, and our polymers can be polyethylene. Okay, so we can just simplify that by going PE for polyethylene. We can also make a polymer called PVC, polyvinyl chloride, and we can also make another one, polystyrene. So those three polymers, the main polymers there, come from ethylene originally, right? So we have to do some modification to ethylene to make these two. But we also use ethylene to make ethanol. Oops, hopefully it's not cut off there. So we're making ethanol, and that ethanol we can do a lot of things with. We can use the ethanol as a petrol extender. So, you know, those of you who are getting very close to driving, you know you have ethanol petrol. We're going to be looking at that. So this is where we're going from here. The first one we're going to be looking at is thermal cracking. Make sure you get that down, and let's look at that in a lot more detail. Okay, the overall process here of thermal cracking, we're going to start off with pentadecane here. Okay, now pentadecane is a liquid, and as we heat that, now what actually happens is that inside, once we have pentadecane as our starting material, we need to heat them up inside a furnace. And inside the furnace they have these coils, okay? And so the coils are called pyrolysis coils. And pyrolysis, lysis means to break, pyro is heat, right? So pyrolysis is the breaking apart of a molecule due to heat, or breaking down due to heat. And so what we're doing is we're heating the pentadecane up to about 900 degrees Celsius. And as we heat stuff up, increase in kinetic energy of the molecules occurs. When the kinetic energy reaches a sufficient amount, then the carbon-carbon double bonds break apart. Okay, so these pyrolysis coils, we have pentadecane breaking apart into smaller molecules. And of course we get a large variation of molecules, right? This is just one reaction that occurs within these pyrolytic coils. But let's just focus on this one. But keep in mind that there's multiple products, all different lengths, but the overall equation is that you're breaking up, let's say, pentadecane into pentane. Then we've got ethylene or ethene. Right, I'm going to be using both names to get you used to them. Okay, so ethylene is the common name, industrial name, and ethene is the systematic name. And we're going to look at that in a bit more detail later, but I'm going to use both terminology here. And then we've got octane. So there is our desired product. Okay, so these two here can be considered as byproducts. So we've got the overall equation there. Now we're going to look at the 3 steps involved in what actually goes on, and we're going to be modelling these in the classroom and making sure you really understand what's going on here. Okay, so get that overall reaction down. You must memorize this. Okay, so flashcards, you know, doing heaps of questions. We need to get this down. This will be an equation that you need to put in your answers when you write long responses in exams. Okay, so write that down, and then we're going to look at the 3 sections. Okay, let's look at the steps here in thermal cracking. Step 1 is called initiation. To initiate something means to start the process going on. And so the kinetic energy of these molecules are quite high, because when you heat them to 900 degrees, they're moving around really fast and they hit each other with a lot of energy. That's enough to break the bond. So you can see here we've got C15, and it's broken between the 7th and 8th carbon, and it breaks. And so we end up with 2 radicals. Now, a radical is a molecule that has an unpaired electron. So let's just draw that here to sort of see what's going on. So if I draw a carbon here, I draw 1 electron. This electron here is bonded to obviously a previous carbon. And sometimes in books you'll see R, which just represents the rest of the molecule. Then we have another carbon with a bond, another carbon here, and that's bonded to other ones. Of course, this carbon here has got a hydrogen here. This one's got a hydrogen, 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 and this is bond to other carbons, for example, right? So we'll just put an R for the rest of the molecule. So these 2 separate electrons will normally bond covalently. Okay, and so we have our complete molecule. However, when the energy is enough, that breaks. Okay, so this carbon here at the moment has got 2, 4, 6, 8. So it feels satisfied. So, but if we break this bond and that no longer is paired up anymore, and I'll just rub this out so you can see. Okay, nice and clean. Here we go. Then we write it like that. And so this is an unpaired electron, and so this is now called a radical, and that's called a radical because radicals are reactive, man. Right? So they're highly reactive, these radicals. So we can see here we've got C15, C7 radical, and a C8 radical. So that step's called initiation. The second step is called propagation. Now, to propagate means to continue, to make more of. So we're making more radicals here. So we've got a C7 radical, and it breaks down further to make a propyl radical. So let's just write that down. Propyl radical. That's how you write them. So here we have a heptyl radical. And of course an ethyl radical, right? So that's called propagation. The last step is called termination. To terminate means to stop the process happening. And so here we have 2 radicals recombining to make a stable pentane molecule. Okay, so that's called termination. So they're the 3 steps there, okay? And in your textbook, you'll see, and in your study notes, you'll see that we're starting from our overall process. Remember, we started off with C15. We wrote it just a moment ago. And that was broken up into a variety of products. We had a propane, we had an ethene, or ethylene, and then we had octane. So they're the end products there. And through this process here of initiation, making the radicals, propagation, the radicals further break down, and then termination, it makes a stable molecule. So I've got some here, for example. This is some molymod kits, and you can see we've got 1, 2, 3, 4, 5, 6 carbons there, so that's going to be a hexane. Whoops, man, of course it just falls apart. And then we have 1, 2, 3, 4, so it's going to be a butane. We have an ethylene molecule here. We've got a double bond. Okay, so that's CH2, sorry, C2H4, right, ethylene. Now, when we make our molecules to make octane, sometimes that we form isomers of octane. So let's just rub this out here, and I'll show you what I mean. So if we have octane here, 1, 2, 3, 4, 5, 6, 7, 8. Sometimes we make isomers. Now, an isomer is a form of a molecule that has the same molecular formula but has a different structural arrangement. We're looking at structural isomers here. If you continue on with chemistry at uni, you'll come across different other types of isomers, such as optical isomers. They look different. So it's really cool stuff. So, but this one here is looking at structural isomers. So there's octane. If we get that carbon and move that carbon there, we form an isomer. So let's move that to there. And so now we have 2-methyl, 1, 2, 3, 4, 5, 6, 7 heptane. So 2-methyl heptane has the exact same molecular formula as octane, but it has a different structural arrangement, and so that is called an isomer of octane. And so when we do this process here, we make octane, but we also make some isomers. And that's going to affect the knocking ability of petrol. So when petrol knocks, that usually means that the pressure inside the cylinders of the car start to increase. And some molecules, this will have a different ignition temperature to octane, and it'll cause the piston to pre-fire and therefore knock. Okay, so pre-firing or early ignition of the chamber causes this knocking effect, and that's called the knocking potential of the engine, right? So this will affect the degree of knocking of the petrol. So that is thermal cracking. I fibbed before because I said the next video is going to be catalytic cracking, but we're actually going to do it now. So make sure you got that down, and let's look at catalytic cracking. Okay, getting ahead of myself there. I wanted to move on to catalytic, but I forgot about our second thermal cracking reason, and that was to make ethylene, right? So we'll get to catalytic cracking in just a sec. I'm getting excited because there's this great molecule I made with Molymod that I want to show you. But before we get that, remember we said that there were two main reasons why we crack petroleum. The first was, of course, to make more petroleum fractions. The second was to make more feedstock of ethylene for important industrial processes. And so we're going to be making it from ethane. So ethane is a refinery gas from the fractional distillation of petroleum. Okay? And so we want to make ethylene. And the reason why we want to make ethylene is because we want to make important industrial chemicals. And we said before that we can make ethanol. And the thing with ethanol is it has a functional group of an OH. So a functional group now is a specific portion of the molecule that contributes towards its properties. And so the OH is the important group or part of the molecule that contributes to the properties of ethanol. So we have an OH or hydroxyl functional group there. So ethanol is very important because industrially it's used as a solvent. All right, we're going to be looking more at that a bit later on, but it's also important as a petrol extender. Right, so when we start looking at the combustion of petrol and combustion of octane versus the combustion of ethanol, we're going to find that it extends the life of the petrol, and we're going to look more into that. The other thing we can do with ethylene is to make monomers. So what is a monomer? A monomer is a single subunit of a polymer, right? It's the basic building blocks of polymers. And if we think about ethylene, if we join multiple ethylene units together, right? So I'll just use simple notation. So there's an ethylene, there's another ethylene, there's another ethylene. So we've made polyethylene, right? And that's very useful for plastics, Glad wrap, plastic bags, etc. So that's an important part of making a plastic or polymer polyethylene. Of course, we have other types of monomers, which of course we have to modify, right? So we're going to change ethylene slightly by adding a group to it. So if we add a chlorine to it, we're going to make another type of molecule that will allow us to make polyvinyl chloride. And then if we add a ring structure to it, we're going to look at this later, but if we add a ring structure to ethylene, we make another monomer, which is going to allow us to make polystyrene. So we can see that these important chemicals here, polymers, plastics are very important in our society. And they all come from, at the moment, they all come from petroleum. Okay, and what we want to do is try and find other ways of making them. Okay, so we don't have to use a non-renewable resource. But anyway, that's some of the reasons why we want to make ethylene from thermal cracking, because it makes a large variety of important, commercially significant monomers and polymers. Okay, I'm using those terms very importantly because they're the terms of the syllabus, and they're the terms that are going to come up in questions, and they're the terms that you are expected to know. Commercially important chemicals. So that phrase should jump into your mind, and you should go, okay, cool. We're talking about polystyrene, PVC, polyethylene, ethanol. All of them come from ethylene, which we can make from the thermal cracking of ethane. That's how you should be thinking, okay? And we're going to be practicing that, and you should be practicing making flashcards, etc., to cascade that information back out. So that is looking at there. If we were to wanted to write a reaction, it would be like this. So we have ethane, and we're going to be making ethylene plus hydrogen. And that occurs at 850 degrees. Okay, and if we were to write, okay, so make sure you got all that down. That is the thermal cracking. Now we're ready for catalytic cracking. Okay, here's the molecule I was talking about. Look at that. Absolutely beautiful. So here we have the molymod structure of a catalyst. And this particular catalyst is called a zeolite catalyst. Okay, so imagine it's like a fine powder, but we have a zeolite cage here. This is what it looks like. It's made up of aluminium and oxygen. Okay, and this cage structure is the basis behind catalytic cracking. You might have heard of catalysts before. In fact, we have talked about them before. A catalyst is a molecule that lowers the activation energy of a reaction to enable it to occur with less energy, and in itself is unused. Okay, and so we have an inorganic catalyst here. For the bioheads, of course, you come across enzymes. They're biological catalysts. But here we have an inorganic catalyst, and it lowers the temperature. So instead of having it at 900 degrees that you need for thermal cracking, we can only have it at 500 degrees. Lower temperature is more economically viable. It's a lot safer. So catalytic cracking is very beneficial. Now, we have here a zeolite catalyst. And a zeolite catalyst, it's an aluminium silicate. Nice if you can remember that, but the big thing to remember is the zeolite catalyst. Lower temperature. Now, it's a honeycomb structure, right? So it's like a cage. So that means it increases the surface area on which a reaction can occur. And as we saw in previous videos, that if you increase the surface area, you increase reaction rate as well. So, you know, we have a lot of reasons why this is making the reaction more efficient. So let's just say we've got a larger molecule here, right? It'd be nice if it's longer. We could make it longer by joining these two together, I guess. And so what happens is the longer hydrocarbons come along and they enter the cage. Right? Remember that this is only a model. It's not size proportionate. In other words, if this was the real size of a hydrocarbon, this would be a lot larger. Okay, but we're just doing this to try and model what's going on. It comes along, it enters the cage and bonds to the surface like a lot of catalysts have. You bond to the surface of a catalyst. That there makes the bonds a little bit weaker. That means that the bonds will break at a lower temperature, and you will then reform, and you'll have, and then the two products will come out. Okay, and so this is unused in the reaction. It can then move along to accept more molecules. Okay, so a zeolite catalyst has those properties like all catalysts, unused in the reaction, lowers the temperature to 500 degrees, and has a large surface area for a reaction to occur. Okay, sometimes you might come across as very porous, so let's write that down. So like the honeycomb structure. Okay, now let's write an equation down. So if we're, let's say, looking at decane, and when we write this, we want to show that it's catalytic cracking by putting zeolite and the temperature. Okay, so they're the reaction conditions that you put on the arrow there. And that makes ethylene and octane. So that's the process of catalytic cracking. All right. Same sort of idea, large hydrocarbon to smaller hydrocarbons, making a fuel-sized fraction in octane, and also making an ethylene that we can use for other processes. But it occurs at a lower temperature, and it's a lot more efficient because it's very porous and increases the reaction rate. So that's it for catalytic cracking. We've covered a lot in this video. Make sure you got your notes, write any questions down, and we can look at those in further lessons and videos. And I'll see you in the next one.